All right, so we're starting a new course in grade 12 chemistry by looking at a unit on the atomic structure. This is going to look at the new model of the atom, the quantum model of the atom, and it's going to be a very, very complicated topic. But before we jump into the new model itself, we're going to start by looking at the nature of light. It turns out that the nature of light itself has great introductory concepts that are needed to understand the quantum model of the atom. So historically, there were two competing theories about the nature of light. Right? The light was thought of by Sir Isaac Newton as being made up of particles, or corpuscles, as he called them. And then competing with that, there was another scientist you've probably not quite heard as much about. His name was Christian Huygens. He believed that light instead should be thought of as being made of waves. And these two scientists lived in the 1600s, 1700s, and their ideas competed with each other. There was evidence and arguments for both of those ideas, but in the end, after lots of debate, it turns out that the wave theory of light was adopted by physicists. Two particular pieces of strong evidence for light as a wave. You might want to write these two down and then look them up yourself on YouTube, because there's some really good videos about these things. One is called Poisson's spots, and the other is Young's double slit experiment, which you'll learn a lot about in physics as well. But if you're interested in the idea of light as a wave and the evidence for it, be sure you write down those two names of those two experiments and then go look them up on YouTube. I may actually post some links on Edmodo as well regarding those experiments. So the wave theory of light, this theory was adopted by physicists in the middle of the 1800s. A guy by the name of James Maxwell basically settled the debate and argued that from here on forward, we're going to talk about light as being made up of waves. When we talk about that, we're saying that not just visible light, but any form of electromagnetic radiation, EM radiation, so electromagnetic radiation, travels through space as transverse waves. So similar as if you were holding a rope and fixed to a wall on one end, and you just started giving that rope a shake, you'd see a wave created along that rope. That's called a transverse wave. This wave is an energy wave, and it can be described with various fundamental terms of vocabulary that you probably studied back in middle school when you talked about waves there. So the idea of the speed of the wave, its wavelength, its amplitude, and its frequency. I should say that as I'm going through this, I'm probably talking faster than you can write, so be sure you can pause the video whenever you need to catch up with your writing if you want. So the concepts of wavelength and frequency are the most important here of those different terms, as well as the speed of the wave, but we'll throw in amplitude as well, just for a more rounded out understanding. When we talk about wavelength of a wave, we're going to use the Greek letter lambda, so make sure you know how to write the symbol as you see, as well as its name, lambda, the letter of the Greek alphabet. We're going to use that letter to represent wavelength in our formulas coming up. The wavelength can be defined in lots of different ways, but a very common one is to say it's the distance between two consecutive crests or two consecutive troughs on a wave. Now be sure that word consecutive is very important. So from one crest in the wave to the very next crest would be a wavelength. In a moment you're going to see a picture. If you're not quite sure what I mean by crests and troughs, you'll see in just a moment. The amplitude of the wave is its height. So if you think of a line going right through the center of the wave, the distance from that line to the top of the crest or to the bottom of a trough is referred to as the amplitude of the wave. Now, both of those concepts, wavelengths and amplitude, which is a height, clearly from their definitions, they're distances. So the SI, the International System Unit for wavelength and for amplitude, will be the meter. Now, we'll often see other units. We'll see things like nanometers and centimeters, millimeters, micrometers, but we'll always need to convert those units to meters when we use them in our mathematical formulas. Slightly harder to understand is the concept of frequency. We're going to use another Greek letter, which is the Greek letter nu. Now you might be tempted to just write it as a letter V, but be careful. V means velocity. So this is a Greek letter nu, and it kind of looks like a V, but the left-hand side of that letter is a straight line, and the right-hand side is a curved line. So it's a little bit distinguished from the letter V or the letter U like that. One way to think about frequency, if you were standing on the side as a wave were to go by you, and you decided to count the number of crests or the number of troughs, or really any particular point that you could count reliably on the wave as it passes by you, you might say the number of cycles of the wave in a certain period of time. So if you counted the number of crests going past in, say, 10 minutes, or the number of troughs in 5 seconds, then you're measuring the frequency. Now, we tend to measure the time interval as just per second. So we're going to measure it as the number of crests or troughs passing a given point in 1 second. Now, the units for frequency, then, if you thought about it, it could be crests per second, it could be troughs per second, it could be cycles per second. So that we don't have to worry about what exactly we're counting, we tend to leave out the numerator in those units, and we just say per second. So the SI unit for frequency is per second, and that could be written as 1 over S, or as S to the power of -1. Now there's another name for that. It's the Hertz, named after a fellow who investigated light originally. So Hertz, HZ, is its symbol. 1 Hertz is the same as 1 per second. They're just different labels for the same unit. There's no conversion in between them. The final vocabulary term was the speed of the wave. So now we're talking about if you were riding the wave, and how fast would you be moving relative to the ground below you or something like that. So here we're talking about, again, electromagnetic radiation, not just water waves or sound waves. And it turns out that light has a very peculiar property. In a vacuum, or in any particular medium, and we're going to just talk about vacuum, the vacuum of outer space, for example, but you could talk about light traveling through the atmosphere, you could talk about light traveling through water. In any particular medium that it's traveling in, light travels at a constant speed, and we call that the speed of light, and it's given a special symbol, the letter C. Now, normally, we talk about light traveling in a vacuum. In all the questions we're going to do in chemistry, we're going to assume that the light is traveling in a vacuum. When light is in a vacuum, its speed is huge. It's 3.00 times 10 to the power of 8 meters per second. So 300 million meters per second is the speed of light in a vacuum. That number is hugely important, and you'll notice I'm giving you here with 3 significant digits. If you look in your data booklet, you'll see a more accurate number there, 2.998 if I recall. So it's got extra significant digits. For all of the problems that we'll do, 3.00 is more than enough significant digits. So here are some pictures just to put those words that you just defined into an image for you. So you can see on the first picture on the left, the wavelength we said was the distance between 2 consecutive crests. And so these points, here's one point on one crest, and here's another crest over here. That distance is a wavelength. If you look on the right-hand side, you can see the wavelength shown there, but notice if you had measured the distance, say, from this trough, this point down here on that top wave, to the very next trough, that would also be a wavelength. So that distance would be the same. You could also measure the distance from this circle point here, where the wave is just going down, crossing the equatorial line, to the same point over here, and that would be another way to measure wavelength. So it's really just a distance between any 2 consecutive corresponding points on the wave. It's just easiest to refer to the crests and to the troughs when you're defining the wavelength. The amplitude you saw there is the height of the wave on the left and on the right. You can see two different amplitudes. Frequency, you can't see it in a picture. So the question here asks which of the waves in the second picture, the top wave or the bottom wave, which of those would have the higher frequency if we assume that they are electromagnetic radiation, so they're traveling with the same speed. Which of those have the higher frequency? You can pause the video just for a moment and see if you can figure out and explain the answer. So we remember that the frequency is, if you're standing on the side watching the wave go by you, it's the number of crests or the number of troughs passing you in a given moment. So if we took this picture over the same time interval and they're traveling at the same speed, we'd have to say that the bottom wave has a much higher frequency because there's many more crests in the bottom wave that are passing you, whereas in the top wave, there's just a handful of crests passing you in the same interval. So the bottom wave has a higher frequency. But if you notice, the bottom wave has a shorter wavelength. Now think about that. So the shorter the wavelength is, the higher the frequency is. So we talk about wavelengths as being short or long. We talk about frequencies as being high or low. So when your wavelengths are longer, your frequencies will be lower. When your wavelengths are shorter, your frequencies will be higher. Now, if you think about that, you might be already making a little mathematical conjecture that sounds like there might be an inverse relationship between them. And in fact, that's going to be the case. There are 7 regions of the electromagnetic spectrum. So make sure you know that term, electromagnetic spectrum. These regions, you have to know their names and you have to know them in order. Okay, you don't need to know the numbers in this picture. Those are wavelengths in centimeters, but you do need to know that the longest wavelengths in the EM spectrum are in the radio region of the spectrum. That could be radio or television signals. Then come microwaves, infrared radiation. Then in the very middle there, visible light. Now you notice that says 10 to the minus 5 centimeters. That's going to be around 10 to the minus 7 meters. Okay, remember that, 10 to the minus 7. In fact, visible light, you might want to note, the short end of the visible light is the violet end of the spectrum, and it's going to be at around 400 nanometers, or 4 times 10 to the minus 7 meters. The longer end of the visible spectrum is right before the infrared region, is going to be the red light in the visible rainbow. And there, that's around 700 or 750 nanometers, or 7 or 7.5 times 10 to the minus 7 meters. So the visible spectrum, I expect you to know the wavelengths on either end. So from 400 nanometers, that's the violet end, up to 700, 750 nanometers, that's going to be the red end of the visible spectrum. Then comes ultraviolet, and you'll notice that you can remember which end of the visible spectrum is which by noticing that infrared will be right next to the red part of visible light, while ultraviolet will be just beyond the violet part of the visible spectrum. And then finally we round it out with X-rays and gamma radiation. Now, if you remember your grade 9 advanced science, you might remember that gamma radiation is the result of gamma decay, a form of radioactive decay, and it's highly energetic and very dangerous. X-rays, you might also be familiar with, are also highly energetic and dangerous, not as bad as gamma radiation, but they're still dangerous. And UV radiation is not quite as dangerous as X-rays, but can also cause cancer, skin cancer, sunburns. So you'll notice as the wavelengths get shorter, the energies of the radiation is getting higher and more dangerous. So the longer wavelengths are less dangerous, the shorter wavelengths are more dangerous to human health. Okay. All right, I'm going to skip over this little slide here, and let's talk about that. Our first really important equation. Okay, so this is going to be your first mathematical equation of the unit. You want to highlight this very well. So we know that, we said a moment ago, that wavelengths and frequencies appear to be inversely related. In fact, they are. If you look at their units, the units for wavelength were meters. The units for frequency were per second. So if you do some logic, if you multiply those together, if you take a wavelength and you multiply it by a frequency, you're going to get units of meter per second. And that sounds familiar. Meters per second, that's speed. So an equation jumps out at us. The speed of light, c, is equal to lambda times nu. Make sure you can look at that equation and read it in that way. C, the speed of light, is equal to lambda times nu, and then understand what that means. The speed of light is the product of the wavelength and the frequency of the light. The speed of light here is going to be, again, 3.00 times 10 to the 8 meters per second. The frequency there will be in the units of per second, and the units for the wavelength have to be meters. So if a question were to give you some other unit like centimeters or nanometers or kilohertz or megahertz instead of just hertz for the frequency, you'd have to convert those units, okay, before you put them into the equation. So we always use SI units in that equation. So highlight it, make sure you've labeled the three letters in the equation, make sure you know what they mean. So a very simple first calculation. As you do this, I want you to write the question down. As always, I want you to write the equation you're going to use, manipulate the equation in your notes, then put your numbers into the manipulated equation with their units, and then calculate the answer and show the correct number of significant digits in your answer. So what would be the frequency of visible light that has a wavelength of 485 nanometers? Now it doesn't say in the question, but we'll assume that this visible light is traveling in a vacuum, so its speed of light is going to be that 3.00 times 10 to the 8 meters per second. Now nanometers, if you're a little rusty on your SI prefixes, you might want to get out your data booklets. And you'll notice on page 2, if I recall, at the bottom of page 2, maybe at the bottom of page 3, there's a table with the prefixes shown there. So when you see 485 nanometers, the prefix nano, you can see in your data booklet, means times 10 to the minus 9. Okay, so the first thing you'd want to do, if you want to pause the video and try it yourself, go for it. Otherwise, I can walk you through this first example. So we want to write the equation for that we're using. So we want to use, you'll notice I didn't do that here in my answer, but be sure you wrote down the equation, C equals lambda times nu. Then I want to see the equation manipulated like you see here. So nu is equal to C divided by lambda. Now that's just grade 9 math manipulation. Pause and think about it yourself. Don't make a silly little mistake right there with some grade 9 algebra. Then you substitute your numbers in, 3.00 times 10 to the 8 meters per second, showing the units. And here you notice what I did with that wavelength. It was 485 nanometers, so I immediately added that times 10 to the minus 9, and then the units are no longer nanometers, now they're meters. If you look at those units just for a moment, you'll see why that was so important, because now the meter on top and the meter on the bottom will cancel, and I'm left with per second, which is the unit for frequency, which means I know that I've set this up correctly. Okay, so I grab my calculator. Be sure you're using the scientific notation button on a graphing calculator. That's the EE button. On a normal scientific calculator, it might be an EE button, an EXP button, something like that. So don't be typing in the time symbol, right? You're typing 3.00 EE 8 divided by 485 EE minus 9. Equals, and you'll get an answer like this, which I've rounded off with 3 digits because both numbers in the calculation had 3 significant digits. 3.00 has 3 digits, 485 has 3 significant digits. So my answer is 6.19 times 10 to the 14 per second. Okay? Now what color of visible light would this likely be? If you were paying attention earlier, you remember that visible light had wavelengths between 400 nanometers and 700 or 750 nanometers. 400 nanometers, we said, was the violet end of the spectrum, and the 700, 750 was the red end. So given that, 485 nanometers is probably a bluish-purple color of light. Okay, it's at the bluish-purple region of the rainbow. All right, so here's another example. Give this one a try in the exact same approach. What would be the wavelength of a radio signal from a radio station WFAE with a frequency, and you can see that that's a frequency when you look at its units, of 90.7 megahertz. A capital M is the prefix mega, right? A little m would have been milli. Milli, of course, means a small number, 10 to the minus 3. Mega, just like it sounds, is a huge number. So if you don't know what mega means, you'll have to look in your data booklet at the table of SI prefixes. So set up your answer in the exact same way that we did the last one. You can pause the video as you're doing that. Okay, so you should have, again, written the equation out, C equals lambda nu. Then you would rearrange the equation as I did here, lambda equals C divided by nu, and be sure if you're getting the habit of always showing your work in this way, when you come to a test or an exam with me, you'll have done it for every homework assignment. You'll just be so used to doing it, it'll be second nature, and you won't be throwing away half marks on a test and then being frustrated that you're not doing as well as you could have. So just build the habit of always showing your work like that. It really makes your notes and your homework much easier to study from, much better to study from, and it means you'll be so familiar with this approach, you'll be working at it so quickly on a test or exam, you'll be fine. So 3.00 times 10 to the 8 meters per second, and the frequency 90.7 megahertz. You saw in your data booklet, if you didn't know it, mega means million, times 10 to the positive 6 per second. You'll notice there I could have put hertz in there, HZ, but I like to see my units canceling, so I remembered that hertz is the same as per second. So megahertz really means times 10 to the 6 per second. So now my units, the per second on top and the per second on bottom, cancel, and I'm left with meters, which tells me I've set this up correctly. So my final answer with 3 significant digits again is 3.31 meters. One last example. Pause the video and try that yourself. So the carbon dioxide is a greenhouse gas. It absorbs infrared radiation. Infrared radiation with a particular wavelength of 0.018 millimeters. Calculate the frequency. So this question will be set up just like the first example. You'd again write your formula, C equals lambda nu. You'd rearrange it to solve for wavelength, that's your lambda. Sorry, the frequency, so we're going to solve for nu this time, my apologies. So nu is equal to C divided by lambda. And then millimeter, there's 1,000 millimeters in a meter, of course, so that means 10 to the minus 3 meters will be what a millimeter is equal to. So you type that in on your calculator, again with the scientific notation button, and you'll get this answer for your frequency. All right, I'm going to pause the video there. This has been an introduction to the nature of light and some simple calculations of wavelength and frequency. We're going to take it a step further. We're going to look at the particle theory of light again, to see why in our next video lesson. And there we'll also start talking about the energy of light. So that's an introduction. There'll be a web assignment on the nature of light as well that you can jump in and try soon.